controller using Kalman's algorithm. Now let us design a controller using Kalman's algorithm for a fourth order process, that is g of s equal to 1 by s plus 1 to the power 4. To design this controller, first of all we have to obtain the mathematical model from the reaction curve. Because it is in fourth order, that's why we cannot use this expression to design the controller. That's why we need a first order plus dead time model is required to design the controller. That's why we are going to model this from the experimental data. First of all we have to obtain the reaction curve. So we got a reaction curve for this 1 by s plus 1 to the power 4. Here the dead time we got is 1.2 seconds and the time taken to reach 63.2% is 4.35 seconds. Therefore the time constant Tp equal to T minus dead time Td, that is equal to 4.35 minus 1.2 equal to 3.15. Let us assume that 4.34, 1.2, that's 3.14. The dead time is 3.14. Sorry, the time constant is 3.14. Time constant is 3.14. Time taken to reach 63.2% of final value is 4.34. If we subtract the dead time from that, then we will get the time constant as 3.14. Therefore the model of the process is 1 by 3.14 s plus 1 e power minus 1.2 s. This is the model. Now we are going to use this model to design the Kalman's algorithm. Now let us assume that the response of the controller is settled after one sampling period. That is, we are going to give a step response. We are going to obtain a step response. That is, r of z equal to 1 by 1 minus z power minus 1 is the input set point. That is, r of z equal to 1 by 1 minus z power minus 1. Therefore, we are assuming that c of k is settled from second sample onwards. At the first sample it is 0, but when k equal to 1, the value is, let us assume that c1. We do not know that value. Let us assume that it is c1. Therefore the response can be written as, at c of 0 it is 0, at c of 1 it is c1, from c of 2 onwards it is 1, c of 3 equal to 1, etc. Therefore c of z can be written as, when k equal to 0 it is 0, therefore c1 z power minus 1, c2 is 1, therefore z power minus 2, c3 also 1, therefore c1 z power minus 1, z power minus 2 plus z power minus 3, etc. Therefore c of z by r of z equal to 1 minus, because r of z equal to 1 by 1 minus z power minus 1, step in. Therefore c of z by r of z can be written as c1 z power minus 1 plus z power minus 2, z power minus 3 plus etc. Or it can be written as c1 z power minus 1 plus z power minus 2, z power minus 3 plus etc. minus c1 z power minus 2, z power minus 3, z power minus 4 plus etc. Therefore all terms after z power minus 3 getting cancelled. Therefore the remaining terms can be written as c1 z power minus 1 plus 1 minus c1 z power minus 2. This is the response. C of z by r of z can be written like this. This can be called as p1 z power minus 1 plus p2 z power minus 2, where p1 plus p2 equal to 1. If the polynomial c of z by r of, if you are able to find c of z by r of z, you will get a polynomial like this. If this polynomial satisfies the coefficients of the polynomial satisfy this condition, then it can be called as p of z. Now let us find what is m of z. Let us see. The controller output is m of z. Let us assume that it is m naught plus m1 z power minus 1 plus mf. From second sampling onwards, the controller output is settled, because the response also settled from second response onwards, therefore controller output also settled. So now let us find m of z by r of z. M of z by r of z is 1 minus z power minus 1 multiplied by m naught plus m1 z power minus 1 plus mf z power minus 2 plus etc. If you multiply this, you will get m naught plus m1 z power minus 1 plus mf, final value of controller output, minus 2 plus etc. minus m naught z power minus 1 plus m1 z power minus 2 plus mf z power minus z power minus 3 plus etc. So from m of z power minus 3 onwards, all getting cancelled because of this negative sign, all getting cancelled from m of z power minus 3. Therefore the controller output m of z by r of z can be written as m naught plus m1 minus m naught z power minus 1 plus mf minus m1 z power minus 2. Like that we can write m of z by r of z. Let us assume that this is equal to q of z. We know that the HGP of z, that is open loop transfer function. Open loop transfer function is equal to C of z by m of z, because open loop transfer function means controller output of the process upon controller output, that is open loop transfer function. This can be written as C of z by r of z, divide the numerator denominator by r of z, m of z by r of z. Already we proved that C of z by r of z is p of z and m of z by r of z is q of z. Therefore HGP of z can be written as p of z by q of z, provided p1 plus p2 must be equal to 1. If this condition satisfies, then HGP of z can be written as p of z by q of z. Also we know that d of z equal to 1 by HGP of z, C of z by r of z upon 1 minus C of z by r of z. This is also we know. This is how we got. This can be derived like this: r of z, d of z, sampler, then 0 order hold, GP of s, then the output is again sampled and through ADC it is given here. So therefore the closed loop transfer function of this can be written as HGP of z. This can be written as, this is h of s. So therefore this can be written as HGP of z. Already we have seen that we have to multiply these two in S domain, then we have to find Z transform. Therefore this is HGP of z. Therefore the closed loop transfer function C of z by r of z can be written as forward path transfer function, that is d of z HGP of z whole divided by 1 plus d of z HGP of z. This is the closed loop transfer function. From this we can find the d of z. So if you cross multiply, you will get C of z by r of z plus C of z by 1 plus d of z h g p of z equal to d of z h g p of z. D of z can be grouped one side, we will get d of z C of z by r of z h minus d of this d of z will group one side, we will get C of z by r of z equal to d of z h g p of z minus C of z by r of z d of z h g p of z. So it can be written as h g p of z d of z 1 minus C of z by r of z. Left hand side is C of z by r of z. Therefore, d of z can be written as C of z by r of z upon h g p of z 1 minus C of z by r of z. This is the derivation for any digital controller. Any digital controller can be written like this. Therefore, we can write already we got HGP of z equal to P of z upon Q of z. Already we got. We substitute in the digital controller D of z equal to 1 by HGP of z, that is Q of z by r of z. Already we know that C of z by r of z is P of z. Therefore, P of z upon 1 minus P of z. P of z getting cancelled. Therefore, any digital controller for Kalman's algorithm is Q of z by 1 minus P of z, provided P1 plus P2 must be equal to 1. If this condition satisfied, we can write like this. Now find HGP of z. HGP of z. Why we have to find HGP of z, that you will see now. In a digital controller, the input is r of z. The error is given to a digital controller. The output of the digital controller should be given to DAC. Then it should be given to a DAC will convert this into a discrete. Here it is digital. Here it will be discrete. That's why the discrete value should be converted into continuous one. For that, a zero order hold is included. The output of the zero order hold is given to the process GP of S. Now it is given to ADC. That's why you get a digital also. So here also you are getting digital. Here also you are getting C of Z, digital value. So it can be compared. Here also it is E of Z. E of Z is given here. The digital output is converted into discrete value. The discrete value is converted into continuous one. The transfer function of zero order hold is H of S. Transfer function of the process is GP of S. If you combine these two, then it is called HGP of S. We know that HGP of Z equal to Z transform of HGP of S, but it is not equal to Z transform of H multiplied by Z transform of GP of S, H of S multiplied by G of S, because there is no sampler between these two. It is a continuous output. That's why here it is discrete. After this ADC also it is discrete. That's why this part alone can be converted into Z transform. Here C of Z, here we are giving D of Z as input, D star of Z as input. That's why between these 2 points only we can obtain Z transform. So these two are continuous. That's why it can be multiplied in S domain. Therefore h gp of z equal to z transform of h gp of s. We know that h of s equal to 1 minus e power minus s t s s upon s. That is h of s. If sampling period equal to 1, then number of sampling period, that is one sampling period. That's why 1 minus e power minus s by s. This should be n. 1 minus e power minus ns by s. The number of sampling period is 1, therefore 1 minus e power minus s divided by s. So hgp of s equal to 1 minus e power minus s upon s multiplied by the model of the process already we got. That is, we cannot use 1 by s plus 1 to the power 4 directly. We need the model of that design the controller. That's why e power minus 1.2 s upon 3.14 s plus 1. If we take z transform of this, h gp of z equal to 1 minus, this can be found separately, 1 minus z power minus 1. Then this e power minus 1, let us assume that sampling period equal to 1 second. Therefore it can be written as z transform of, this can be taken outside, 1 by z power minus 1, z transform of e power minus 1 s, 1 sampling period, e power minus 0.2 s upon s multiplied by 3.14 s plus 1. So now this also can be taken outside. Therefore 1 minus z power minus 1, z power minus 1, z transform of e power minus 0.2 s upon s 3.14 s plus 1. Here this 0.2 is fraction of sampling period, intersampling period. 0.2 is not integral multiple of sampling period. That's why we must go for modified z transform. We have to go for modified z transform because this 0.2 is less than sampling period. Therefore we have to find m equal to 1 minus dead time divided by sampling period. That is equal to 1 minus dead time is 0.2, sampling period is 1. Therefore 1 minus 0.2 equal to 0.8. m equal to 0.8. Therefore hgp of z equal to 1 minus z power minus 1, z power minus 1, z modified, because we cannot take conventional z transform. We have to find a modified z transform because it is the dead time is not integral multiple of sampling period. Therefore we have to go for modified z transform. For that m equal to 0.8, m equal to 1 minus dead time divided by sampling period, that is 1 minus 0.2 by sampling period is assumed as 1 second. Therefore 1 minus 0.2 by 1 equal to 0.8. Therefore z modified equal to z power minus 1 upon 1 minus z power minus 1 minus e power minus before going for this we have to write this we know that z modified z transform of 1 by s multiplied by s plus a by z modified z transform a by s multiplied by s plus a equal to z power minus 1 divided by 1 minus z minus 1 minus e power minus a m z power minus 1 upon 1 minus e power minus a z power minus 1. This is the formula we know for modified z transform. Now we are going to use this. Here m equal to 0.8 and a equal to 1 by 3.14 equal to how much? 0.3184. Of h gp of s equal to what we have 1 minus e power minus s upon s multiplied by e power minus 1.2 s upon 3.14 s plus 1. This can be written as h gp of z equal to 1 minus e z power minus 1 z transform of e power minus s e power minus 0.2s. We are separating this one point into two parts. One is integral multiple of sampling period, another part is less than sampling period, that is 0.2s upon s multiplied by 3.14 s plus 1 is a transform of. So this also can be taken outside, therefore 1 minus z power minus 1 1 minus z power minus 1 z power minus 1. So 1 by 3.14 is z transform of e power minus 0.2s multiplied by 0.318 s multiplied by s plus 0.318. Gp of z equal to 1 minus z power minus 1 z power minus 1 z transform of 0.318 e power minus 0.2s z mod z transform of 1 minus s multiplied by s plus 0.318. So here a equal to 0.318 and m equal to 0.8. Therefore h gp of z equal to 1 minus z power minus 1 z power minus 1 z modified z transform is z power minus 1 1 minus z power minus 1 minus e power minus m equal to 0.8 multiplied by 0.318 1 minus e power minus 0.318 z power minus 1 z power minus 1. So this can be written as 1 minus z power minus 1 z power minus 1 we take LCM 1 minus z power minus 1 1 minus this is equal to how much 0.727 z power minus 1. This can be written as z power minus 1 minus 0.77 z power minus 1 0.77 z power minus 1. If we take LCM, if we take LCM h gp of z equal to 1 minus z power minus 1 z power minus 1. LCM is 1 minus z power minus 1 into 1 minus 0.7727 z power minus 1. Here 1 minus 0.727 z power minus 1 into z power minus 1 minus 1 minus z power minus 1 multiplied by 0.77 z power minus 1. So these two are getting cancelled, therefore z power minus 1 denominator is 1 minus 0.727 z power minus 1, numerator is 1 z power minus 1 minus 0.727 z power minus 2, that is minus 0.77 z power minus 1 plus 0.77 z power minus 2. So z power minus 1 minus 0.77, that is 1 minus 0.77 0.23 z power minus 1. Here 0.77 minus 0.727, this is plus 0.043 z power minus 2. So 1 minus 0.727 power minus 1. I should have done for z power minus 1. We have to add these two, to make P1, P2, we have to add these two, 0.23 plus 0.043, 0.273. We have to divide the numerator denominator by 0.273. So we will get 0.23 by 0.273. 0.84 z power minus 1, 842 plus 0.043 divided by 2.73. 0.158 z power minus 2. இதை டிவைட் பண்ணோம்னா 1 by 0.273. 3.663 minus 0.727 by 0.273. 2.66 z power minus 1. We got this. Therefore, P of z equal to 0.842 z power minus 2 plus 0.158 z power minus 3. If you add these two, P1 equal to 0.842 and P2 equal to 0.158. If you add these two, you get 1. Therefore, this is P of z. Therefore, Q of z equal to 3.663 minus 2.66 z power minus 1. Therefore, the d of z equal to q of z upon 1 minus p of z, that is equal to q of z, that is 3.663 minus 2.66 z power minus 1, 1 minus p of z, that is 0.842 z power minus 2 plus 0.158 z power minus 3. ಇದು ಮೈನಸ್ ಆಗಿದೆ ಬಿಕಾಸ್ 1 minus p of z, minus 0.842 z power minus 2, 0.158 z power minus 3. Therefore, d of z can be written as, multiply the numerator denominator by z power 3, we will get 3.663 z power 3 z power 3 minus 2.66 z power 2 divided by z power 3 minus 0.842 z power 1 minus 0.158. That's all. So this we have to enter as a controller, a digital control system. So here we select a discrete transfer function for digital controller. We selected a discrete transfer function for digital controller. The output is not continuous, that's why we have to include a zero order hold after this discrete transfer function. Then the transfer function, what system we are going to control? We are going to control the 1 by s plus 1 to the power 4. So if you write 1 by s plus 1 to the power 4 in polynomial, you will get 1, 4, 6, 4, 1 as coefficients. If you put all these values in the denominator, you will get the transfer function 1 by s plus 1 to the power 4. So we entered. Now we have to enter here the controller, digital controller in z domain. So d of z equal to 3.66 minus 2.66 z power minus 2. So the coefficient of z power 1 is 0. We entered the coefficient of the constant term also 0. The denominator, the coefficient is z power 3. Z power 3, that is 1. Then coefficient of z power 2 is 0. Coefficient of z power 1 is minus 0.842, and the coefficient and the constant term is 158. 158 SAT. These are the coefficients we entered. Now digital controller is ready. Now let us simulate. We are going to control this with the conventional PID controller. Already we tuned for this process in the previous experiment, that can be taken as a reference. So now we are going to compare these two responses. So if you simulate, you get the response like this. So yellow is the digital controller. It is smarter than PID controller and it quickly settles. Therefore definitely you can notice that the ISC value is 1.8 for PID controller, 4.6. It is less than the PID controller. So the Kalman's controller gives better response than a conventional PID controller tuned by Ziegler-Nichols. You can notice that IAE also smaller than this. So the important thing we have to note here is to enter digital controller we have to select the discrete transfer function module from the library. That is the only difference. After the discrete transfer function we have to put a zero order hold because the output of the discrete controller is discrete values. Therefore to make it continuous we have to put a zero order hold after this. That's all. That is the only difference. Now let us simulate for load response. For that we have to make step value equal to 0. That we made 0. Here also we have to make step value equal to 0. Then let us make this load equal to 1. Step time is 0. Final value is 1. Similarly here also we will make step time is 0. Final value is 1. So we are giving a step load to this system. For that how it behaves let us check. So this is the magenta is for PID and the yellow is for this Kalman's controller. Definitely the Kalman's controller settles quicker than a PID controller. Therefore the ISE, IAE will be definitely less than this. Let us notice. ISE value for discrete controller, that is Kalman's controller is 0.79. whereas for PID controller is 0.8. We can notice that we got lesser value for ISE. Similarly IAE for PID controller we got 3 and here we got 2.6. So from this ISE IAE values we can understand that the Kalman's controller works better than a PID controller tuned by Ziegler-Nichols. In the same way we can check the ISE IAE for servo response also. That also gives better response than PID control tuned by Ziegler-Nichols tuning boards. So, okay.